Hi guys, welcome back to a new IMONST video. So in this video, we'll be talking about problems 18 to 20 of the junior section, and then for the senior paper will be questions 13 to 15. So basically we're just finishing off the junior paper. Let's look at the first out of these three questions. Given a right-angled triangle with perimeter 18, so let us draw a right-angled triangle over here. Then we label the sides A, B, C. So from the first sentence, we know that the perimeter, so it's A plus B plus C, equals to 18. And then the sum of the squares of the three side lengths is 1 to 8. So A squared plus B squared plus C squared equals to 1 to 8. What is the area of the triangle? The area will be AB divided by 2. Now, since we have a right triangle here by the Pythagorean Theorem, Pythagoras Theorem, we would have A squared plus B squared equals to C squared. So from here, we can turn this into 2C squared equals to 1 to 8. C squared equals to 64. Then we square root both sides, take the square root, we will have C equals to 8 because lengths are never negative. So from here, using this one, we can turn this one into A plus B plus 8 equals to 18. A plus B equals to 10, and then B, we can let B equals to 10 minus A, right? So our figure has an ABC, right? So now we just have 8, A, and 10 minus A. So our area of the triangle would be A times 10 minus A divided by 2. Yeah, something like this, which is 10A minus A squared divided by 2. Now, what we see here is we would have A squared plus 10 minus A squared plus 8 squared, which is 64, equals to 1 to 8. Then we will have A squared plus 100 minus 20A plus A squared equals to 64. Now, we will have A squared, 2A squared minus 20A plus 36, because we minus 64 by both sides, equals to 0. Then we will have A squared minus 10A plus 18 equals to 0. Now we see something very similar over here. What we can do is what we will do is, let me go down a little bit. I'm so sorry for. Okay, what we will do is we will find A squared minus 10A minusing both sides by 18 gives us negative 18. Then we reverse it, meaning 10A minus A squared will give us negative 18, which is positive 18. And since our answer is to be divided by 2, we will have 10A minus A squared divided by 2 is 18 divided by 2, which is 9. So the area of this triangle is just 9. Okay, so I hope you guys understood my process. Now let's move down to problem 19. A perfect square ends with the same two digits. How many possible values of this digit are there? So the same two digits, meaning something like 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, and then 9, 9. So 10 of these, how many of these are feasible, right? So one thing, if you know what mod is, as I have explained in the previous videos, one way to determine whether a number is a square number is by using mod 4, right? So mod 4 is just divisibility by 4. So any any square number would be congruent to either 0 or 1 mod 4, modular arithmetic. You can check it out on the web if you haven't listened to my previous videos and do not know what it is. So why is this so? Because 2k squared, even number squared, is just 4k squared, which is a multiple of 4, and then 2k plus 1 squared, which is obviously an odd number squared, is 4k squared plus 4k plus 1, which is a multiple of 4 plus 1. So we need to see, since we can just check the divisibility of 4 of these numbers, because if you want to determine if a number is divisible by 4, we also can just check the last two numbers, as you can see here. Why is this so? You might think for yourself, and then you can tell me in the comments what you've thought. Why do we just need to check the last two digits to see if it's divisible by 4? Okay, now for 0, 0, it is obviously a multiple of 4 because it's 100k, is 4 times 25k, right? So 11 then will be congruent to 3 mod 4. And then I'll just use these two apostrophes to represent mod 4. 22 will be congruent to mod 2. 33 will be congruent to mod 1. Then 44 will be congruent to mod 0. Okay, so mod 4, mod 4. 55 would be congruent to mod 3, mod 4. And then 66 congruent to mod 2. 77 congruent to mod 1. 88 congruent to mod 0. Okay, so mod 4 again. Then, okay, and then 9. So for 99 would be congruent again to 3 mod 4. So as we have said before, any a squared can only be congruent to 0, 1 mod 4. So 2s or 3s are just eliminated, right? So we will have this one out, this one out, this one out, this one out, this one out. So we're just left with 0, 0, 3, 3, 4, 4, 7, 7, 8, 8, right? But then there is also this fact that says the units digit of any a square, any integer squared, is either 0, 1, 4, 5, 6, 9. Okay, so only these 6. Why did I say so? You can also verify for yourself. I will not explain further. So as you can see here, we have 0, 3, 4, 7, 8. Then we have only 0 and 4 satisfy these conditions. So 3, 7, 8 are then again eliminated. And then we want to find examples of these numbers of perfect squares that ends in 0, 0 or 4, 4. Very easy. We just take where is my pen? We will have 10 squared equals to 100. As you can see, it ends in 0, 0, and then 12 squared is 144. Also ends in 4, 4. Okay. So how many possible values of this digit are there? In short, the answer is just 2. Okay. So hope you guys got it right. Now let's move on to the last question. Now, so for problem 20, find the sum of all integers n that fulfill the equation 2 to the power of n times 2 to the power of n times 6 minus n is equal to 8n. Okay, so we want to divide our integer types into, like, say, about 2 categories. Okay, so we want to divide it into 2 categories because what we want is, okay, let me write down first. So our first category is that n is smaller than 0, which is negative numbers. Negative integers. Right. So for negative integers, so we would have 2 to the power of n is smaller than 2 to the power of 0, which is 1. But so for example, if you say 2 to the power of negative 1 will be 1 over 2, 2 to the power of negative 2 is 1 over 2 squared is 1 over 4, and such. As you can see, no matter the power, 2 to the power of n will never be smaller than 0, okay? Will never be smaller than or equal to 0, okay? So 2 to the power of n is always larger than 0. So we see that this 8n when n is smaller than 0, 8n is just smaller than 0 because it's just multiplying a negative number by a positive number, so it's also a negative number. But then you see, if 6 minus n, okay, wait, if n is smaller than 0, negative n would be larger than 0, then 6 minus n is definitely larger than 6, which is larger than 0, right? So we have a positive number here, we have a positive number here, it comes out a negative number. This is not possible, right? So this case where n is smaller than 0 is basically not applicable, okay? Now, we want to go to the second case, which is n is larger than 0, meaning the positive integers. Okay? Now, this one, we will have to branch it further into another 2 more subsections. So I'll just draw another line here. Something like this. Why do we need to do so? Because we know from here, when n is larger than 0, then 8n is also larger than 0, right? So we need to branch this into 6. 6 minus n is larger than 0, and then 6 minus n is smaller than 0, okay? Because this one makes all the difference. As we said before, 2 to the power of n, no matter the power, is always larger than 0. So if 6 minus n is larger than 0, and then this one is a positive number, so we will have a 2 to the power of n, this one is positive, then 6 minus n, this is also positive, equals to 8n, this is positive, so this is doable. Now, we have 2 to the power of n, if we have 2 to the power of n, sorry, positive, and then 6 minus n, being smaller than 0, it's negative, then we will have 8n, which is positive, so this is contradictory, so we need to cancel this out. This case is not applicable, right? Since 6 minus n, we have confirmed that it is over 0. This means that 6 is larger than n is smaller than 6, and then we also said before that n is not negative, so 0 is smaller than or equal to n, and then n is smaller than 6, so we would have n could be either 0, 1, 2, 3, 4, 5. Now, since we have eliminated so many cases and we have 6 cases left, the only thing we have to do is just plug in one by one, right? So if we plug in n equals to 0, then we will have 2 to the power of 0, and then 6 minus 0 equals to 8, 0. So we will have 1 times 6 equals to 0, which is not correct, obviously, so wrong. So this is not applicable. N equals to 1, 2 to the power of 1, then 6 minus 1 equals to 8 times 1. So we have 2 times 5 equals to 8. Again, wrong, so this one is also not applicable. Now, for n equals to 2, 2 to the power of 2 times 6 minus 2 equals to 8 times 2. So we would have 4 times 4 equals 16, which is correct. So this is one of the cases. Then n equals to 3, 2 to the power of 3 times 6 minus 3 equals to 8 times 3. We have 8 times 3 equals to 8 times 3, so this is correct. So 3 is also one of the cases. Then n equals to 4, we would have 2 to the power of 4 times 6 minus 4 equals to 8 times 4. So 16 times 2 is 32, correct. So 4 is also one of the cases. Lastly, we have n equals to 5, 2 to the power of 5 times 6 minus 5 equals to 8 times 5. Is this correct? So we would have 32 times 1 equals to 40, which is not correct. So this one is not correct. So we have 2, 3, 4 as our only cases. So what are the sum of all the integers and that fulfill the equation? So we just need to add up 2, 3, and 4. 2 plus 3 plus 4 is just 9. So we have solved question 20. Now, we have finished the junior papers, and then for the senior paper, we have 5 questions left. So this is the video for today. If you guys have any problems, you can write down in the comment section below. I'll try my best to answer them, and we'll see you guys in the next video. So, ciao, ciao.